Okay, here we will be solving exponential equations. There are two types of exponential equations, really two different ways to solve them. I like to call them the easy ones and the hard ones. The easy ones are the ones where it's possible to write both sides using the same base. And then we'll use the property that the exponential function is a one-to-one function. So if you ever have a raised to the x equals same base raised to a different exponent, the only way that's possible is if those exponents are in fact equal. Exponentials are one-to-one functions. If the outputs are the same, the inputs must be the same. So as a silly example, if I had 2 to the x equals 8, well, I could think of this as 2 to the x equals 2 to the third power. I have the same base. So in a sense, we're not really canceling, but it's kind of like we're canceling out these bases. And we can just say x must equal 3. In a sense, all we really did was we just converted to logarithmic form here. We just thought, oh, well, log base 2 of 8 equals 3. It's really all we're doing, converting to logarithmic form. Okay, so let's say we had this equation here. First thing we ask ourselves, is it possible or easy to write both sides using the same base? Can I write 9 as a power of 3? Or can I write 3 as a power of 9? And the answer to both is yes, pretty easily. So we'll use 3 as our common base. 9 is just 3 squared. Okay, now I have to remember rules of exponents. I have a power raised to a power. I can't just cancel out the bases here. This is a 3, that's a 9. 3 squared is 9. I have to distribute this 2 here. A power raised to a power, we multiply. So I'll get 3, and my new exponent, or my rewritten exponent, will be 2x minus 8. Just 2 times x, 2 times negative 4. Now I have the same base. Now, in a sense, I can kind of cancel the 3's. We're not really canceling. We're using the fact that we have the same base, so we set the exponents equal. And now it's just a linear equation. We just solve it. Move this x over, we'll get x over here. Move the 8 over, we get 9. And you could check this yourself. Plug 9 in to both sides. You should get the same thing. And we can kind of look at it. We'll get 3 to the 8th. Over here, we'll get 9 to the 5th. Now we get messed up there. 9 plus 1 is 10. 3 to the 10th is the same as 9 to the 5th. Okay, another one. Very similar problem. You're tempted, I know you're tempted here to be like, oh, let's cancel out a 4. You can't do that. You can't cancel anything here. These order of operations, if I divided this side by 4, I would have to lower the exponent down by 1. And that gets awful. You don't want to play with that. Can I write both of these, 4 and 8, using a common base? Yeah, I can. I could use 8. I could use 4. 8 is 4 to the 3/2 power, but I don't want to deal with fractions. I want to use a common base that's simple. Well, 4 and 8 are both powers of 2. So 4 is 2 squared. 8 is 2 cubed. Notice how I'm writing parentheses here. These are pretty necessary. A power raised to a power, we multiply. I have to distribute here. This is where the mistake happens. You have to distribute. On the left, I'll get 2 to the 6x minus 2. On the right, we'll get 2 to the 3x plus 6. Now I have the same base. I can set the exponents equal. 6x minus 2 equals 3x plus 6. So if we subtract 3x, we'll get 3x. Add the 2 over, we'll get 8. So x equals 8 over 3. And we're done. Okay, now sometimes it's not easy or even possible. Technically, it's always possible, but sometimes it's really hard to write both sides using the same base. So let's say we had an equation like this. Well, this 3 is multiplying. That 3 is not being raised to an exponent. I could divide both sides by 3. These 3's do cancel. Over here, I'll get 400 equals 4 to the x. And now I could try to write 400 as 4 to some power. Well, yeah, clearly 400 could be written as 4 to some power. That's what I'm trying to find. But it's not going to be easy. So I don't want to try that common base stuff. I want to use logs. This is what logs were invented for, to solve this problem. Well, one option is I have base 4. I could say take log base 4 of both sides. On the right side, log base 4 of 4 to the x, those are inverses. They cancel out. That's rule number 6 from the rules of logs. That log base 4 and 4 cancel out, and I get x equals log base 4 of 400. That's the answer. Essentially, all I did was converted this equation into logarithmic form. Here's exponential form, here's logarithmic form of the same equation. It's what logs were invented for. But I don't have a log base 4 button on my calculator. If I wanted to try to approximate this, get some decimal approximation, my calculator won't do log base 4. So let's do that a different way. 4. That's a perfectly fine answer, but I want something I can type in the calculator. So we have 400 equals 4 to the x. In our calculator, we have common log, log base 10, and natural log. I'm going to use natural log, honestly, because it's less writing. Instead of writing log, I get to write ln. So I'm going to take the natural log of both sides. I'm allowed to do that. Natural log is a perfectly good function. Over here, natural log and 4 to the x, those are not inverses. This guy has a base of e. This is a base of 4. But what I can do, rules of exponents, rules of logs, say I can pull this exponent down to ground level. So now I have x times ln of 4. To get rid of that ln of 4, I can just divide it out. And I get x equals ln of 400 divided by ln of 4. Now, you might be looking at that and think, oh, well, what rule of logs can I use to simplify that? So go back, look at your rule of logs, all 6 of them. Look and see which one has log divided by log. None of them do. None of the rules of logs will let us simplify this. There is another way we could write it, though. I mean, here we have it. They're right next to each other. This thing must be equal to this thing. We call that the change of base formula. And this says, if you ever want to write log base b of, let's say, m in a different base, say you want to convert to log base c, then it would be log base c of m divided by log base c of b. The way I remember this formula is just geographically. I know it's a fraction. The m is physically higher than the b, so the m goes on top. The b is physically lower, it goes on the bottom. Okay, so switching from here to here, which we've essentially just proven we could do. Log base 4 of 400, if I wanted to throw that in my calculator and use natural log, it would be natural log of 400 divided by natural log of 4, which is what I've written. Okay, let's do some more complicated problems. Okay, this is going to look nasty, but literally every one of these are exactly the same. First thing we try is finding a common base. There's some number that I could use and say 3 and 5 are both powers of the same number. Not easily. So we're going to use logs, and I'm going to use natural log. You might think, well, I'll take log base 3 of both sides. Sure, go ahead. You'll get the right answer, but it's not going to help over here. I've got a 5. Log base 3 of 5 is not going to be anything pretty. So I'm going to use natural log just so I can type my answer in my calculator at the end. So I will take natural log of both sides. The whole point of taking logs, anytime you take a log, the purpose is to get all the exponents down to ground level. So all these exponents will come down. 3x minus 1 comes down to ground level. Okay. Now, this natural log of 3, this natural log of 5, those are just numbers. You could type it in your calculator if you want. It's just some horrible decimal. That's multiplying. That's multiplying. I can just distribute. Now, normally, if I had a 7 here and I distributed, you would write 7x. But if I write ln of 3x, it looks confusing because you don't know if I write this, you don't know if I mean natural log of 3 times x or if I mean natural log of 3x. It gets confusing. So we're not going to write it like that. I'm going to say x ln of 3. But that's just a number times x. It's just like saying x times 7 instead of 7 times x. And the same thing here. 4 plus, that's a plus, 4 natural log of 3 equals, same game here, distribute the ln of 5, but I'm going to write all the logs on the right side of each term. So I'll have 3x ln 5 minus 1 times ln of 5. 1 times ln of 5 just being ln of 5. Okay, now I have 4 terms. 1, 2, 3, 4. 2 of those terms have x's in them. 2 of them do not. I'm going to get everything with an x over on the left-hand side. So I'm going to take this guy, move him to the left. Everything without an x, move to the right. So this guy's on the left, he's going to stay on the left. This guy's moving over, so he'll become negative 3x ln 5. This guy's already on the right. He's going to stay over there. This guy's going to move over. He was positive, so on the other side he'll be negative. So I just moved some terms around. I still have 4 terms. Now, on the left side, I've got so many x's and so many x's. Essentially, all I'm doing right here is combining like terms. I have a common factor of x here. I'm going to factor out that common factor of x and write down what's left over. Factoring out that x, I'll be left with ln of 3 minus 3 ln 5. I didn't do anything on the right side. It stays the same. Now that's just a number multiplying x. If I had 12x equals something, to get rid of the 12, I would divide. So that's the last step here, divide by whatever that number is. Remember, that's just some number. That's all that is. And over here, of course, those cancel. And I get x equals this nasty fraction. And that's the final answer. Now you may be thinking, oh, well, let's use rules of logs and try to combine these together. Like maybe bring this 4 in, bring this 3 in as an exponent, add it inside, or add it outside becomes multiplied inside, subtracted, blah, blah, blah. You could try all that. Nothing pretty is going to happen here. In this case, I'm telling you, it's not going to get any better, so just leave it like that. If you need a decimal approximation, your calculator is smart. As long as you're careful typing this in, you could type it in your calculator and get a decimal approximation. Okay, let's do one more example. But I want to know how many of my students are actually watching these videos all the way to the end. So if you're listening right now, this is what I want you to do. I want you to write in your notes right here, +5 extra credit points. And show that to me next time you see me. And then don't tell anyone about it. Don't even tell people in your group. Write down right now, +5 extra credit points. And when you see me, show me, and I'll give you 5 extra credit points just because you watched the video all the way to the end. Okay, let's solve this guy. We're going to do it the same way, taking natural log of both sides. The whole point of taking logs is to bring the exponents down to ground level. So exponent 2x plus 4 comes down to ground level. This exponent 3x plus 5 comes down to ground level. We distribute these logs. When you write it down, write the log on the right side of each term. So distributing, we get 2x ln 7 plus 4 ln 7 equals 3x ln 9 plus 5 ln 9. Distribute, distribute. We got 4 terms. 2 of them have x's, 2 of them don't. Get everything with an x on one side, everything without an x on the other. I always take the x's to the left side. So this guy will come to the left. That guy has no x, he goes to the right. We get 2x ln of 7. He goes to the left, becomes minus. This guy was already on the right. I'm going to write him down. This one moved to the right. On the other side, he'll be negative. At this stage, everything on the left side has an x in it. Factor out the common factor of x. Write down every other symbol. Basically, just write this without the x's. And that thing is multiplying x to get to the other side, divide it over. And there is the solution. Okay, right now should be popping up some other relevant videos, rules of logarithms, logarithmic equations, and so forth. Click on any of those videos for similar topics.